I've been talking about number theory again, and we'll keep switching back and forth with this. So the fundamental theorem of arithmetic, well, so the controversy from last time was is one a prime number? So our official textbook says that, well, it doesn't say specifically, but the way it's kind of diplomatic about it. So a number, well, just as well let me write it up. So a number is an integer is called prime, or a prime, if its only divisors are 1 and itself. Well, x. An integer x is called, and this is how the book handles it, larger than or equal to 2. It's diplomatic because they are not saying that 1, you still could call 1 a prime number if you want to. Okay, so that's the definition. So here then in my statement of the that was messy of the fundamental theorem of arithmetic, you got to say factors other than 1. Okay. So 1 does count as a factor, right? The factor, anything that divides the number, is its factor. So 1 is a factor. But as far as the uniqueness part of the theorem, this is the two parts, frequently the case. So not only there's the decomposition, factorization of an integer, but also it is unique up to an order of the. I think I want to say this, probably, by order of the factors. There is a point here too that might be sometimes also there is some confusion about it. It's how to read definitions, and what I mean is a definition is also a proposition, a statement, right? And it has an if in it. Okay. If, as you recall, is the arrow. Which way does it point? This if over here. No. If the only divisors of x are 1 and x, then it is called the prime. Okay, but since it's not a regular, it's not a theorem, so actually it is, even though we do not have an extra f there, it is always understood both ways. Okay, so you go back and forth. It is to two identical statements. That's the idea of a prime, to come up with a replacement of some complex idea, more or less complex idea, with a 1 or 2 words. Okay, so it's an abbreviation, and it has to then work both ways. So if and only if is presumed. Okay, so that's that little if here is presumed to mean if and only if. Okay. Okay, so in that case, how would you put it? The x restriction, x larger than or equal to 2, is a bit out of place. So it means that the definition does not extend to numbers 1 or less. Okay, which is fine, really. So we do not speak of numbers. For example, you cannot speak of real numbers as prime or not prime, right? So just as well. It only applies to, so just as well add 1 to that class of numbers that is not an issue, not the subject to this definition. Okay. Okay, so this is a nice theorem. Okay, it is really a fundamental theorem. One, we can utilize it to study fractions. Well, so fractions. How can we use the fundamental theorem for fractions? What does a fundamental theorem, which isn't entirely about integers, how does it help us with fractions?
Tell you when they're reduced?
Yeah, that's right. So that's right. So not only that, so this is yeah. So let's have a definition. So what's the definition? A fraction, which is p over q, p integers, pq integers, with q not equal to 0, is called reduced when what? Or if. Well, you brought up reduced fraction, so what does it mean?
If both numbers are prime?
No, not necessarily. What is a reduced fraction?
Would be the smallest factor, smallest greatest common denominator.
There's a simpler way to make that idea. Reduced, what does reduce? There's a verb there, to reduce. What does it mean to reduce?
Simple.
What does it mean to reduce a fraction?
The integer on the top and the bottom don't share any factors.
Right, that's the way to put it. Okay, so that is reduced. So reducing meaning simply canceling factors, dividing both numerator and denominator, right? So 15 over 10, right? So it is 5 times 3, 5 times 2. I cancel 2, I have 3 over 2. So this one is reduced, right? And this is the reducing, or reduction, whatever you call it. This is the process, okay? Canceling factors, and now we know that we could cancel one prime factor at a time, but the general idea is this: so reduce if p and q have no common factors. Once again, I want to say not equal to 1, but at some point it becomes redundant, repetitive. Okay, incidentally, this is called, they're called, not prime, but they call mutually prime, because they don't have to be both prime. So I could have 20 over 21. So this one is also reduced, but neither numerator or denominator is prime. The point is they have no common factors. They're called mutually prime or relatively prime. Okay, and so now we can speak of factors in a more and reducing factors in a more consistent way, because now we can concentrate on prime factors, and so that gives us the beginning of our reducing factors process. Is a factor. So if you have given a p and q, factor p and q into primes, okay, to begin with, and then cancel the repetitions, right? And the result is a reduced fraction. Right? Okay. Now, so that is what I want to mark here is this, the existence part of the fundamental theorem. So there is a factorization. How does the uniqueness help? What does uniqueness tell us? So there's only one way to factorize p and q, and therefore there's only one way to cancel those factors. So there's only one reduced way, reduced fraction. Okay, so reduced, and there is no other way. There is no other reduced fraction. Reduced fraction equal to p over q. Okay, so you can certainly get the same fraction for from different non-reduced fraction, but once you get there, there is no way to have another reduced fraction represented. So in other words, what does it mean? It means that the fractions are how should I put it? It's unique. They're unique in general, representing fractions. Every fraction can be represented by its reduced form in only one way. Okay, so that's what it's supposed to mean. What helps us also, this little analysis, so this is for uniqueness. That, by the way, I'm not sure if you've seen this. Well, probably. Have you seen this notation? Well, it's just for fun. There exists only one. That's what it means. So exists with exclamation point means not only there's existence, but that existence is unique. Okay, so that's sometimes is used for. It's not a part of the of logic really. It's just an abbreviation. So anyway, I want to use this information and go back to square root of 2 being irrational. So and recognize there is a way to slightly alter our proof. Remember this? The beginning of the proof of square root of 2 is irrational. So then it is a smart idea just to, instead of jumping to p over q, just to say that how about it is reduced to begin with. So suppose p over q is reduced, right? Because every fraction has a reduced form, and so it's equal to it. So just as well, we can assume that we did all the reduction, and we have a reduced fraction. Okay, so then you see the consequences it produces. Then I have, as we did, square root of 2q is equal to p 2q squared is equal to p squared, and what? And then we continue with the logic that we did. Remember what at this point we did? How the proof proceeded from this point on. What?
P squared is even because it's 2 times q squared.
No, it was about p being even or odd, right? So we conclude then that because it's the same number. Okay, so think in terms of fundamental theorem. And it's the same number. There's only one factorization. We actually implicitly made that conclusion in our analysis, which is same number. So the 2 in the left-hand side is practically the same number. So there's only one factorization of that number into integers. Okay, so it means that there is 2 on the left. Then there is a 2 on the right. Okay, so which proves that indeed that p squared is even, and then p is even. And then the problem becomes, and then this is how I could proceed. P squared is divisible by 4, or how about divisible by 2 squared? Okay, then 2q squared is divisible by 2 squared. Once again, factorization. So if 2 is present, then on the other side 2 is also present. But because of the square, p squared is divisible not by 2 by 2 squared, which means that 2q squared also divisible by 4. Okay, and then what? And by the same logic, what's the conclusion? Q, what do we know about Q? well, 2q squared is divisible by 2 squared. So q squared, what? Is divisible by by 2. Yeah. So once again, we count the prime factors, and the list of prime factors is one and the same. So if if there is a 2 appears twice on the right, then it appears twice on the left, which means q squared, which means that that's why 2q squared has to be divisible by 2 squared. But then if we reduce 1, that 2 over there, we're just canceling out those primes, and we conclude that q squared is divisible by 2. And then once again, we conclude that q is divisible by 2. Okay, and finally, well, in other words, it's so it's even. What's the conclusion? P is even and Q is even. We did not see it as a problem then. It was not, and now we have a different angle. So, what's the problem? What's
If they're both even, then they can be reduced.
That's right. So we have, in other words, we have arrived to a contradiction, because the assumption was that it was reduced. The fraction was reduced to begin with. Okay, so the proof is pretty much the same. The only difference is, remember that part of the proof of the square root of 2 being irrational was this reduction of as we went down with those p's and q's, down and down, and then we said, well, there at some point the process will stop, and that's how we arrived to a contradiction. But this one, that part is taken care of by the fundamental theorem of arithmetic. So we just start with all the everything has been reduced already, and so we arrive directly to a contradiction through a list of sequence of conclusions, right? So very straightforward conclusions. As there is no extra information. We did have a lemma. Remember that if p squared is even, then p is even, like that. But once again, the fundamental theorem helps with that too. So it's very helpful, really. So it's certainly slightly longer than what you can do it in your mind. It's probably much quicker than that. Okay. So any questions about this? Okay, so next I want to do the division with remainder. So I mean, when you have two common factors, when we have a fraction, so and it is reduced, suppose, and then in the meantime it's not reduced all the way, so it's not an integer. Reduced but not an integer. So sometimes you can go on and then you end up with an integer. So when everything is cancelled out, the q is totally cancelled out, and then you have your integer, right? So when the number of factors of, well, so let me. Then what can you say about the list of factors of list? It's not a set. List of factors of p. List of factors of q. What's the relation? The relation when under this assumption. So we have the fraction is the fraction does not reduce to an integer. So it doesn't really matter that it is a. So a fraction is not an integer. hold on a second. No, what it is an integer. What if it is an integer? Okay, so that's the assumption. So suppose P over Q is an integer. Then what's the relation between the list of factors of P, list of factors of Q?
List factors of Q are a subset?
That's right. That's right. But just keep in mind, it is a subset, but even though these are not exactly sets, unless you think of them appropriately, because they could repeat themselves. So for example, we have 8, and I list its factors. It would be a mistake to say just the factor is 2. The factors are 2, 2, and 2. Okay, so in that sense, these lists will repeat factors if they are repeated if they appear more than once. Okay, so in that sense, so the kind of elements of these two sets are not necessarily unique. So which means that they're more lists than sets, but they still make sense. So you can reduce everything when there are more factors in the numerator than in the denominator, and every factor that appears in the denominator also appears in the numerator. Okay, but suppose that's not the case, then we want to actually carry out the division, and since P over Q, and since there is no full reduction, it's not an integer. So what it's going to be? It's going to be well, let's say, hold on a second, what is it? The notation is R, no. Okay, sorry about that. Let's start over. A over B. A over B. So B will remain in the denominator, and this will be Q over here. Okay. Okay, so I don't know, like 8 over 5 is equal to 1 plus 3/5, right? Proper versus improper fractions. So if you prefer that way. Okay, so that is the point of why this might be necessary, but really we don't want to deal with fractions anymore. So what we do is we write it out as A is equal to QB plus R. Same. So this one is an integer with respect to integers only. Then it becomes clear what we're talking about. So there are these names for all of them. R, certainly you realize, stands for the remainder. Remainder, and Q is the ratio. Ratio? I think it's ratio. Or is it the quotient? No, the ratio is the ratio, so it is the quotient, right? Q is the quotient, that's what Q stands for. Quotient. B is the divisor. And A is... What? No, the dividend. So you don't really have to remember all of them. I keep forgetting as you can see these words, but the remainder certainly is what we care about. The R is the remainder, so division might be carried out completely, so it's pretty much the issue of factoring or reduction, the same thing, right? So if there is no R, then we just reduce our fraction over A over B into one integer, B, Q, which is the quotient, okay? So if R is equal to 0, R equal to 0, A is equal to QB, or A over B is equal to Q. Okay, so that's entirely about factorization, and nothing else is going on. But generally, the remainder is what we're looking at. So that's what stands in the way. So I wonder if you have seen anything. So what does it have to do with anything outside of number theory? you kind of do this on a daily basis if you think about the decimal system. So if I have a number 337, okay, what is the meaning of 7? What's the meaning of 7? What?
7 tenths.
No, there are no tens. But yes, it is 7 is the remainder of division by 10. Right? Okay, so if we move on, and every integer, every rather decimal has the same meaning here, or similar. So what's the remainder of division by 100? What? No. 37. 37. Okay, so that's roughly how it works out. So you divide by larger and larger powers of 10, and then you just progress by adding one extra integer every time. And so to begin with, that is the decimals, and then slightly more exotic example is the binary. So if you want to represent a number in terms of binary, what do? You divide by powers of 2. Okay, so what is, for example, what is the last digit? Even though it's not appropriate, calling digits refers to 10. Maybe, is it? Maybe. Well, that's a digit of 337 in the binary. What? 1. 1. So you divide by 2. Divide 337 by 2, and it will be 2 times whatever number we don't know plus 1. Okay, so that 1 is what's left. Then what is the next digit? You divide 337 by 4, right? And then whatever is left there goes into the next digit. Okay, so we'll look into that later. But I'm not sure if the ancient Greeks were thinking about binary numbers, probably not, but really or decimals. They didn't have decimals, so they weren't thinking about that. They were thinking about fractions, I think, for the most part, fractions and integers. So they did this, and they just to ensure that this is possible to carry out in the first place. So that's the issue we're gonna address, and the by which I mean, yes. So why is it always possible to represent any integer a in this manner? So given integer a, given integer b, why is it always possible to represent it in such a way? So one extra requirement here is, let's not forget that r is the remainder. It has to be less than b, larger than or equal to 0. Okay? So division with remainder is always possible. How? So why always possible? And the answer might lie in division by subtraction. Are you familiar with that idea? I think it is. I think they teach that now. That's how they teach in 3rd grade to divide. Well, if you didn't see it, I certainly didn't. So divide 22 by 5. Or do you subtract 5 as many times as necessary? So 22 minus 5 is equal to 17. Then 17 minus 5 is 12. 12 minus 5 is 7. And finally, 7 minus 5 is 2. Okay? So until the process stops, that you keep subtracting. Okay? And then, okay, so what have we achieved with this little computation?
4
A remainder 2, that's right. So this is my remainder. And the quotient is 4. That's right. So the number of steps, 1, 2, 3, 4. This is my, so remainder R, and this is quotient Q. So we could write then that 22 is equal to 5 times 4 plus 2. So you subtract, well, you can 22 minus 5 times 4 is equal to 2, right? That's what we have accomplished. And then the final representation is 22 is equal to 5 times 4 plus 2. Okay? So 2 is the remainder of 2 divided by 5. Okay? So that is the idea of pretty much how it works. It's called the Euclidean algorithm. So subtracting little by little, and so I hope you can already see that it should work. It should work. So you have 2 integers, A and B, and what do? You start subtracting. And you subtract as many times as necessary. Okay? So we just have to put it, so given A and B, subtract B from A as many times as necessary. Okay, so that's the plan, the algorithm. Okay, so we just have to write it up in such a way that there would be no doubt that it works out. The process is not dissimilar, so it's certainly described here on the right. The idea is there, but you also remember that that process in the proof of the square root of 2 is irrational is how you start with a certain equation and you revisit that, not revisit, recreate that equation with a lower, smaller and smaller numbers. Okay, and then it going down, 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 and then you know it's going to end then because you're going to hit 0 or something sooner or later, which means that then your process is done. So that's pretty much the same. Certainly that little computation indicates that there's no other way for this to happen. Okay. Okay. So let's try to carry it out. And remember, like I said, we create the equation every time. What is the equation? The equation is the same as the one I have over here, except we could, okay, so A is equal to BQ plus R. The requirement, the final requirement is, so we still want this relation, but the final requirement that R is less than or equal to B might not be accomplished until you're done. Okay, well, you keep subtracting, and as you can see, these are R's. These are R's, right? And the equation is satisfied, but the remainder is not small enough for it to be called the remainder. It has to be less than the divisor, otherwise it's not a remainder. So then this is the equation I want to reproduce, and A and B are fixed. What's going to be changing is I'm going to be assigning a subscript to these 2 integers, Q and R. Okay, and then we'll be going down the way we already have seen. So let's go this way. Hold on. So that's the still question. But what I'm doing here is A minus B. A minus B is my, what is it? It is, hold on, what is the idea? So we can certainly just go and subtract, and this we'll call this R1. Okay, so that's the process that I have described over here is what we want to accomplish. R1, R2, R3, and finally when we arrived at, after 4 steps, we arrived at R4, that is our remainder. It is, until then, 2 was not less than less than 5, and so we could not stop. Also, we do not proceed from 2. And in fact, there could be, if we subtract 5 one more time, we're going to become negative, and we just stop there. Okay, so that's the idea. We start with a minus b, and call this R1. Okay, then you can see what has happened here. I take my R1 and subtract a one more time, b one more time. So like this, R1 minus b, and call it R2. Then I take R2 minus b and call it R3. Okay? So what's the conclusion is? The conclusion is that the process has to stop because before the number becomes negative, or at least when Rn, let's say R sub q is equal to, let me put it this way. So it will be, after a few steps, I'll have RQ minus 1 minus b is equal to RQ. Okay, so you see it's the same process, subtracting v as many times as necessary until what? Until this number is less than or equal to strictly less than b. Okay, in the meantime, the previous one was larger than or equal to b. Okay, so larger than or equal to b, that's the assumption. Every time you're subtracting, it is still larger than or equal to b. And then at some point, at less than b, then we stop. Okay? So then steps. Step 1, step 2, step q. Okay, so let's just, how do we put these together? Well, we can substitute one into the next, I suppose. Maybe the best way just to do it is just to substitute one into the best, or yeah, you don't have to raise your hand.
Should your R on the right side just be less than B? On top right?
Yeah, over here. Yeah, I want only. Yeah. Okay. Okay, so I need to figure out the processes here. The fact that it ends is obvious. We just need to prove that what we have accomplished, what we found RQ, so we declare now let R be is equal to RQ after this many steps. Now we need to prove that what we have found is correct, so our equation is satisfied. So what we have at the top, A is equal to BQ plus R. So everything is satisfied. We certainly know that Q is an integer, R is an integer, A and B were given. So why is this satisfied? Well, you see how we can prove it? Enough room, but well, how about we'll look into substitution. I'm going to no, vice versa. I'm going to substitute R1 in the first equation into the second equation, like this. Okay, so what do I get? I will get A minus B equal to minus B is equal to R2. Okay, A minus B is equal to R2, right? Or simply A minus 2B is equal to R2. Okay, and then I take that R2 and substitute it once again. Okay, so what is the result? Another substitution. Well, I have my arrow in the wrong direction again. Sorry about that. I take R2 and substitute it here. What's the result? R2 is equal to a minus 2b, substitute, what do I get?
Get a subtraction of one more b, so it'd be a minus 3b.
That's right, a minus 3b is equal to R3. So as you can see, the equation themselves are very, very much similar, if not identical. So this one, so this is the first one, this is the second one, this is the third one. So the ones that I underline, you can see what's happening. Every time the index on the right changes, so R progresses from R1 to R2 to R3. Okay, then A remains, and the index is the same as the factor of B. So after Q steps, over here, I will have what? After Q steps, what is my equation? A minus QB is equal to RQ, right? So after Q steps, right? Right? And that's the same. So we have what we wanted. Okay, so once again, this is called Euclidean algorithm. Okay, so it's used a lot in different settings. The ideas also will reappear as ultimately the idea that we used of when we proved square root of 2 is irrational was something similar, and I think it is maybe this was the originally where the idea came from. Okay, so then the division with the remainder is possible to begin with, and it is produced the same result naturally. So instead of division giving you one number, it gives you two, the quotient and the remainder. Okay, so this will be the foundation of the so-called modular arithmetic. You're familiar with modular arithmetic? So it's like decimals. You can do algebra with decimals, but well, actually, what I meant to say is that the binary, you can do binary integers, and there are only two of them. So the algebra of modular arithmetic it's the algebra of remainders. So we already saw something like that when we did logic. See, for example, 0 plus 0 is equal to 0, but, and then 1 plus 0 is equal to 1, 0 plus 1 is equal to 1, but 1 plus 1 is equal to 0. Right, so this is entirely about even and odd, right? So even, odd, and we already know the rules between them. So even plus even is even, but odd plus even is odd. Odd plus odd is even. But what is it? It's simply about what you do with arithmetic with remainders of division by 2. So division by 2. So and then you can actually carry out this algebra with these remainders, at least with addition, and then we'll see there's also multiplication is also possible. So we're gonna do that later, but I wanna stop and just keep switching not gears but topics. I want to look into calculus a little bit, and calculus 1. I'm not sure if it'll help you with calculus 3, but I want to look into beginning of calculus 1 and some definitions and some theorems, and just not prove anything really, but look at the logic as well as things such as contrapositive converses of all the theorems that we face. So we'll get back to that, to modular arithmetic, shortly, but I want to do a little bit of calculus. Well, this one actually is usually appears in calculus 2, limits of sequences. So suppose we have a sequence, say AN. So be careful with the notation of sequences. By the way, we put the braces on as if it is a set notation, but it's really not. because the order matters. It's not a bag of numbers. A sequence is not a bag of numbers. It's ordered sequence. So one after the next or the next. If you rearrange them, the result will be could be entirely different. Okay, so let's not make no mistake like that. So and this sometimes the language becomes loose, and so a sequence is given, and then you say, I want to define the limit. Okay, the limit is the limit of an, sometimes you omit the rest of them, is such a number, L, that, do you remember the definition? Well, it actually starts out the same way. For any epsilon greater than 0, what? Well, the delta is the limit of a function. So this one is for sequences. So as we progress along the axis of n, the values of n, we should be getting closer and closer to L. So there is no delta, but rather there is an n. So there is an n such that for all n larger than n, an minus L is less than epsilon. Okay, so this is how, if you give something like that on a test in calculus 2, you probably will be okay. But this is quite a mess actually. If you look at it carefully, a lot of mess there. And one is to begin with is certainly you want to be very strict about the logic that we have discussed. So writing in terms of quantifiers helps. Fortunately, this is not too hard. For any epsilon greater than 0, there is an n. Okay, so as always, we have started. Then you can either proceed to say, once again, for any n larger than n, certain statement is true, like this, or you can have an implication. So if n is larger than n capital, then this inequality is satisfied. But it's really not the problem. The problem is where you see where the problem is. Well, the limit is defined as a number that satisfies a certain property. Okay, do you see mismatch of in the grammar? You see problem with the grammar? Well, we'll discuss that later, but this is the problem. So when you state the definition, you don't know how many numbers like that would satisfy the property. So that needs to be discussed. So we'll do it next time.